So here, if I can count, is the third of my LED lamp teardown videos. And in this one, I've got these four mains voltage lamps. Now, I think these could be a little bit more challenging to get inside, so I thought I'd show you them intact before I actually start tearing them apart, because once I'm ready to show you the innards, they might not be quite so recognisable. It'll be interesting to see what sort of current limiting or control circuits they've got in them. I suspect they may all have a simple capacitive current limiter like the original GU10 that I showed you before. I've got another GU10, but I'll leave that for the moment. So first of all, we've got this quite nice LED filament lamp. I think these are quite attractive, and so I thought I'd get one of these not that long ago, but it didn't actually last very long at all. Now, if I can find my magnifying glass, here we are. I can't quite see the writing on it. It's Wilco 6.7 watts, 240 volts. Well, it had to be that, 220 to 240 volts. 806 lumens, that's the key thing. 2600 degrees K, made in PRC. So like all of these, made in China. Now, I'm not quite sure how to get into this. Breaking the glass could need a little bit of care, because I need to get inside and get those filaments out. The other problem with this is that each of those filaments probably takes about 70 to 100 volts. Now, quite how I can test those without having live mains on my desk, which I really don't want, I'm going to have to do a little bit of thought on that. Come back to that one. Okay, we've also got an R80 reflector. Now, getting into this, the initial stage was very easy. I found that I could just pry off this cap, and you can see a disc containing, can't remember how many, quite a few of these lead packages inside. It should then be possible to get this out as a metal. I think it's glued in there. I'm going to have to, whether I can just pry that out or I'll have to cut some of this away, I'm not quite sure. So that should be relatively easy. Now, these two bayonet cap, they're going to be a little bit more challenging. This one has got quite a lot of metal on it, which is encouraging because that's maybe designed to dissipate some of the heat. In fact, it's got some of these vents in here, which is encouraging. Nevertheless, it didn't last nearly as long as it should have done. And this one, it says on it, Lemnis lighting, Ferox LED dimmable. Well, it'll be interesting to see what the different circuit inside a dimmable one is. It says 6 watts, 230 volts AC, and some kind of serial number or model number there. This one I did say, did I? Yes, this one is Lightwell E27 R80, yes, that's the shape and the size. 85 to 265 volts, 2700K. That's a very wide voltage range, which means there's going to be some slightly more sophisticated control circuit in there, not just a simple capacitive dropper. So this one, spoken about that, and then this one, it says down on the bottom there somewhere, another Wilco one. Wilco are cheap, but I'm losing faith in them. 15 watt, 2700K, 1521 lumens, I think, also made in PRC. I think I needed a slightly more powerful one. I forget where I actually had this, but it didn't last nearly as long as I was expecting. I thought maybe this bit was plastic, but I think it's actually metal. When I started initially trying to pry, you can see the silvery aluminium along there. Hopefully I can get this bulb off, which will be a start. Then I'll have to see what I can do with a bit of brute force and ignorance and see how we get inside those. Okay, so this is just a preliminary, and it'll be a few days and I'll come back and hopefully we can actually look at the insides of some of these. Okay, so taking these bulbs roughly in reverse order, I started off with this bayonet cap one here. This was a little tricky to get inside. I started off by trying to pry open the bulb at this point. Didn't seem to have very much success, so I tried some of my Loctite glue remover, but unfortunately on a convex surface like this it just ran all over the place. That glue remover is probably intentionally very low viscosity, so that didn't work terribly well, but in fact I did manage to open up a little crack at one point, and in fact if I'd persevered with the glue remover, this probably would have come off in one piece. But anyway, I decided to take a hacksaw to it, and I cut around here, and then I was able to open it up. And inside we've got this array of a whole load of these LED chips. Well, in fact, the 4 groups of these 6, so 6 fours are 24, and another 2 makes 26. So the first thing to do then is to see if we can test those. This, in fact, the wires were soldered in there, the wires coming through there and soldered into there, so I had to cut those off. The solder didn't seem to melt very well. I think it's very high temperature solder. So we take this off. That came off, and in fact it was the wires holding it, really stopping it sort of flapping about, but there was some glue or some sort of heat sink compound there, so take that off. Now, I don't think I showed you last time my little LED tester, which perhaps I did, I forget. You can find this on my Instructables page. All it consists of is a USB plug, which I've got plugged into this USB power pack. And here we've just got a 220 ohm resistor, no, that's 330 ohm resistor, and some pins so that I can easily connect things to it. I can plug an LED into there if I want to. So if I just want to test a few LEDs, this is quite useful to have. So if I try this on any of these LEDs, let's see if we can get them to light up. Yes, that's lighting up. And that one too. That one too. Now, if you look very carefully at this in the right light, I don't know whether you can see this. Let me bring it up close. See whether you can actually see it. If I get the light on it in the right direction, it's quite tricky to see on camera, I think. But you can actually see. Let me put it down again. If you look very carefully, you can see that the power comes into one of these. Okay, it comes into there. Okay, so if we start with that connection there, that track goes up to there through that LED, and then through that LED, then through that one, through that one, through that one, through there, through there, through there, then through there, and it goes through to there, there, and there, back through there, then it goes through all the LEDs on the other side. So we've actually got all of those 26 LED packages in series. Now, we want to know what voltage each of those LED packages is. So if I connect up my meter as well, if I can get everything into, let me put that, take those bits away, put that over there so you can see it. Switch it on to the 20 volt range. connect the probes to the pins. Okay, that's it. Now we should be able to, that's actually showing 5 volts, which is actually the battery just going straight through this resistor into the into my probes. Now I can't quite remember which way round this went. The battery voltage is currently 5.17. Now if we, okay, and it's dropped to 5.04. So there's 5.04 volts across that LED. So that's not one chip, that's obviously 2 in series, and each LED would be typically about 3 volts. So that would normally take about 6 volts, but it'll just light up. That's not nearly as bright as it would be normally, but with 5 volts, it's sufficient just to illuminate it. Okay, so we've got 26 LEDs, and each of them is going to be something like 6 volts. So 6 times 26, I think, is 156. Yes, 156. 156, probably rather more volts for the entire array. Okay, so let's clear that out of the way. Right, so back to this. So we've got 150 odd volts there. So what's the controller look like? Well, actually, before we do that, getting the rest of this apart was a little bit tricky. I've got a photo which I'll put on the screen now, which shows you what happened when I took the bulb off. And here we are, and you can see actually inside, you can see that the whole thing is completely potted with some kind of, it turned out to be some kind of rubbery compound, which has obviously filled that. Now, it turned out to be possible to gouge out some of that rubbery stuff with my letter opener, but not completely. So I then took matters into my own hands and got out my Dremel with a cutting disc on it, an abrasive cutting disc, and cut down the sides, hoping to open it up and hence get the works out. Didn't work quite that easily, but having got it open that far, I was then able to scrape away the rest of the potting, rubberized potting compound, probably a silicone or something like that. Then getting this, was the base was still on, so getting the base off was a bit of a challenge. So there again, I found that my abrasive cutting wheel cut through the metal quite easily, and with a little bit of effort, I managed to tear this open. The little pin on the other side stopped it coming apart very easily, so I had to cut around that in order to open it up. And then we've got that, and there were just 2 wires going from here into there. Well, examining this closely is obviously a slightly more sophisticated circuit than 1 or 2 of the previous ones that we've looked at. We've got a little transformer or something here, got a big capacitor. On the other side, you can see the, let me bring it up close, you can see the regular bridge rectifier. In fact, in trying to gouge this out, I damaged that and broke the connections there, but we should still be able to test it. Also, looking very carefully, some of these connections, let me bring it up close again. A couple of these connections, it looked as though the solder joint was not good at all. Can I focus this? Is it going to focus? Yes, there it is. That solder joint has obviously failed. It was a dry joint, and the one on the other side as well. This one here, that had also failed. And in fact, there's a solder joint here, which obviously that, through bending it in order to get it out, that is broken, but it shouldn't break like that. So it looks as though part of the problem could well be poor solder connections. See just one or two little bits of the rubbery compound which I haven't managed to get away. Okay, so that was part of the problem at any rate. Whether that's why it failed is difficult to tell. Now if we can get the number on that chip, is it the other way around? Will it go any closer? Yes, it is the other way around. I was right to start off with. So that says BP3216. Well, on these chips, it's always very easy to refocus. You can always look up the number on these chips in Google, and you'll usually get quite a lot of these all data sheet websites, a number of them which collect hundreds of, no, thousands, many thousands of data sheets. I don't like those websites too much, because they often give you a lot of completely irrelevant device data sheets with similar sorts of numbers. So if you can find the manufacturer's data sheet, or a data sheet on the manufacturer's site, that's generally very much better. With companies like TI and Maxim and a lot of the commoner ones, you can actually get the manufacturer's data sheet, and that's much clearer. So I managed to get that, and I'll put that up on the screen, and we can actually see the data sheet. Let's have a look. Okay, let's talk that through. So on the right-hand side, no, let's start with the left-hand side. Always start with the left-hand side. There's the regular bridge rectifier and a smoothing capacitor. This is an example circuit. I don't think this is actually quite the same as we've got here, but it shows how this chip is meant to be used. Regular bridge rectifier provides something like 300 volts DC into this BP3216 chip. On the right-hand side, we've got two connections marked drain and two marked CS. We've got a switching transistor in there. Now when that switch is on, the current goes through from the bridge rectifier, through that little resistor, and hence through the inductor, and then down through the LEDs on the right-hand side. Now, as I said last time, the inductor acts a little bit like a momentum, so it takes a while for the current to build up, and once it gets up to a certain level, the switch in the chip switches off, and then the current can continue cycling around that loop, going back through that diode all the way around as the current dies away, as the momentum of the inductor gradually, or not so much the momentum, it's actually the magnetic field in the inductor dies away. And once it gets down to a certain level, the switch switches on again. An example of, or an analogy of how this works is a bit like if you were dribbling a football down the street. You don't push it all the way, you keep giving it a little kick, and in between kicks it just carries on rolling under its own momentum. So this circuit works in very much the same sort of way. You give the momentum in the coil a series of regular kicks, which keeps the current continuously moving. The rest of the circuit, okay, so you've got a connection through from the left-hand side of the coil, and that is the feedback, and that resistor is able to give the chip a measure of the current which is actually coming through there. Okay, so let's go back to the actual device, the actual gadget itself. Well, first of all, I need to get out my my component tester. Well, actually, before we do that, let's see if we can check out that bridge rectifier with the test meter. Okay, so we'll put it on the diode range, switch it on. I've still got it connected up to my LED tester. There we are. Okay. So now, can I see which of the outputs of this is positive and which is the negative? Not easily. So I'm going to have to put there on one of the outputs and try the inputs in turn. The AC inputs. Doesn't seem to be anything there. Try the other one. And if that didn't work, this one should. Okay, I think because there we are. Okay, the leads broke off right against the plastic chip, so we can. I was actually putting the pin on the broken lead of the device, and that didn't work. So if I put it on the stub of the pin here, if I can get it, yes, that said difficult to get hold of, 5.88 or something, which is the, there we are, that's the, so between there and there we have a diode going that way, and if I change these over, now from here we should have two diodes going in the opposite direction. Once again, if I can get this onto the stub of the broken pin, right, 5.84, sorry, 0.584, 0.587, so it's something like that. So here we've got two diodes going there and there, and two diodes going there and there. Okay, so that's the positive output, and that's the negative output, whichever way the polarity is of the mains coming in. So that seems to be okay. We've got two of these Schottky diodes here. Let's try testing those. Now, from what we did last week or last time, they give a much lower voltage. Looks like it's the other way around. .481. The other one, I think, last week was 0.3 something. Okay, so that Schottky diode is okay, and let's try this one. Don't think it was that way round, but I was having trouble holding this still. There again, 0.484 volts. So the two diodes are okay. What else have we got on here? So we've got several surface mount resistors. We could test those. These beige coloured devices, these are capacitors. One there and one there. So we can actually test those with the little device component tester. Okay, so that's still in the drawer, so I'll get that out and pause this video just for a moment. Okay, so here we are. I've got the little component tester out now. Battery 8.14 volts, that seems to be okay, no component found. Well, obviously the first component to test is this electrolytic capacitor. Well, in fact, there's two more bad solder joints there because that's just wobbling about. I lifted this up in order to get the filler out from underneath. So let's see if we can get this onto. In fact, don't need those pins. Let's just put this and connectors directly onto the leads of the capacitor. That's that one on there. In fact, this capacitor doesn't seem to have any markings on it. Whether the silicone filler has sort of dissolved those off. It doesn't even seem to have a plus or a minus, but the board marking, you can see there, that line down there, that indicates the negative side of the capacitor. Okay, so we got that on fairly securely there. Let's press the button and see what it says. Probing. Okay, 150 microfarads, 0.91 ohms, that's pretty good. And the IL, that's the leakage current, is 18.87 microamps. Well, there's nothing wrong with that capacitor at any rate. That looks fine. Now this little joker here, haven't seen one quite like that before. Now if we look very carefully, let's see, there seems to be more than just an inductor, because I think it's actually a transformer. There's some more of this. It looks like there's two leads going into it there from one winding, and I'm pretty sure there are two more leads going into it from that winding. So that's actually a transformer, or it would appear to be. And on that side there are two solder connections there, and those are the presumably the secondary, and that's the primary. So this is a slightly different design from the example circuit that was shown. Possibly that's in order to get up a step up of voltage in order to drive those 26 LED chips in order to get 150 plus volts in there. Okay, so let's see what the component tester says about that. This is going to be a little bit more tricky. Now, if I were to invite you round, you could press this button for me, but don't know where you live anyway. Okay, so it looks like those two are the primary connection. A bit more light on this. That's better. I can see it better. I don't know whether you can. Now, can I touch those on there? I haven't got any spare fingers for the button. Right, that's it. Okay. Probing. Right. 1 ohm and 42.82 microhenries. I don't think I explained last time that inductance, which is the measure of the momentum of a coil, is measured in henries. I'm not quite sure who Henry was. I'm sure you could look it up on Wikipedia. Okay, so that's the primary, 42 microhenries, and the secondary, once again, if I can get that on there, that on there, and find a finger to press the button. What's this going to say? It's obviously not making contact. Try again. Definitely doesn't seem to want to make contact. Okay, the contact's there, okay, on the tester. Try one more time. Right, okay, this time it just says 5.84 ohms, so it hasn't recognised it as an inductor. Okay, that's interesting. Well, definitely both those leads go into the coil, so that would indicate that that's actually, what was the other one in ohms? I can't remember. So that's a 5.8. The other one was only 1 ohm, I think, wasn't it? Let's check again, I forget. So on there, seems to go on to shut down. Let me disconnect the battery and reconnect it, reboot it. Okay, so going back to the primary. There again, that's only showing resistance 0.96. Well, previously I think it was 1 ohm, wasn't it? Yes, it's not showing any inductance at all, perhaps too little. Yes, I'm pretty sure it was only 1 ohm that side, and this side is 5 ohms. Oh, okay, this side is 2000 microhenries, 5 ohms. Okay, right, so this is being a little bit unreliable. So we've got a much higher inductance on that side, which means that it's got more turns, which means that there's a step-up ratio between there and there. Both the resistance is about 5 times as much, and the inductance, whatever it was there, is much less. So that's a step-up transformer. Now, there's no way we can actually test this little chip. The only way you could possibly test it would be to put it in a similar circuit, but that would be very difficult. So the only other thing we could do would be actually to test those resistors and capacitors. Well, just as an experiment, it's very unlikely that any of those have gone, though of course it could be a solder joint problem again. So if we try and test that one there, and press the button. Okay, that's interesting. So it's found, this is the problem if you try testing components in circuit. It's found a diode there. That's definitely not a diode, that's a capacitor. So it's found a diode which is connected between those two points on the circuit. A reverse current of 897 microamps, a capacitance of 0 proof, so it's got minimal capacitance. So that is obviously going through a diode elsewhere in the circuit. You can probably see it. Could well be going through that diode there. So testing capacitors and resistors in circuit is not very reliable. But anyway, those things, unless there was any sign of burning, there isn't, it's extremely unlikely that they would have failed. Well, it's not impossible, but it's most unlikely. And likewise, the little transformer, there's no sign of overheating or burning there, so that would seem to be okay. So my conclusion is that it's probably a matter of these poor solder joints, or it could be that in fact as this warms up, I think quite often it happens that these LED chips test okay, but obviously we're not giving them their full voltage and power, and hence they're running a lot cooler than they would actually in practice, and not giving them time to warm up. So that is that lamp there. There was just one other thing in the base. We had this resistor, which I think turned out to be 47 ohms. I measured it, and I think that is simply to limit the inrush current as you switch it on, because otherwise when a capacitor is initially discharged, it'll take a very heavy current if you connect it straight across a voltage. So that's just to limit the initial current as you switch it on. Actually, just coming back for a moment to this little transformer, we were getting unreliable readings for the inductance of the primary and the secondary, and it occurs to me that that's almost certainly simply because of the other components in the circuit. If you try and test the windings of a transformer in circuit, you may well get unreliable results, because in a sense the transformer is a bit like a telescope. If you put a resistor on one side of the transformer and measure what you can see on the other side, depending on which way the telescope is and whether it's a step up or step down transformer, you'll see that resistance either magnified or reduced. And so when we didn't see an inductance, we were just seeing magnified or maybe reduced the resistance on the other side. So that's something to be aware of. Likewise, if you've got a voltage on one side, it'll obviously have to be an AC voltage because DC doesn't go through a transformer. But if you've got an AC voltage on one side, the other side will see that either magnified or reduced according to which way round it is, step up or step down, like looking which way through you look through a telescope. And if the voltage is increased, then the current that it will be available will be reduced, and likewise. Well, actually, look at the time. I think I'm going to have to leave this next one until another session. This one was very interesting, much the most sophisticated circuit of them all. And there's a little bit of a mystery on this one, which we'll come to. I wonder if you can spot it. Can I focus? There we are. I wonder if you can see what that is. We'll come back to that another time.